thanks for having me. Happy to sort of be here and chatting about some of this.
And also there are folks over the Zoom.
Sure, I can try to, yeah. I can try to make sure I can see them. Let's see. Oh, there we go. Don't know if, okay. So if people have, I guess we might want to minimize it though. So actually keep it minimized so that you can see the screen.
That's okay. I just remind you, if there will be more, the welcome actually was larger.
Yeah. If there's any questions, let me know. But yeah, so great to, for those who virtually and those in person, talk about this work. Feel free to stop me at any point, by the way. Like, I hope this will be a dialogue, honestly. It's work I'm really interested in. I think it's really relevant. So feel free to sort of pause me at any moment. So let's make sure I get this to go right like that. Perfect. Okay, so this is my agenda. Don't need to memorize or anything because we'll come back to it throughout the talk. But I just want to sort of give you a roadmap of what we're going to be doing. We'll kind of come back and see where we are at every point. And my hope is that every step in this agenda, I've convinced you of something, and sort of we can move forward to the next thing I try to convince you of. So the first thing I'm going to try to convince you of is that this actually is a relevant problem. Like this is an important problem that we should be thinking about. And so let me tell you what the sort of the context of this is. So the motivation for all this work is that it begins with the fact that machine learning modeling allows for us to extract useful information very efficiently, almost automatically from large amounts of unstructured data. So like just getting information from data at a really high scale, right? And we've seen research take advantage of this, right? We've seen things like people using machine learning models to get sentiment from large amounts of corpuses of text, right? Again, very large amounts of data, getting it very efficiently and getting it pretty accurately. We've seen folks trying to use images to get demographic data about folks in images. Again, large amounts of data gets a signal from images now. There's this paper in PNAS which basically shows that you could take Google Street View data and build models and actually accurately sort of estimate what the demographic makeup of a neighborhood is. And just for comparison, sort of a survey study that would allow us to get the same level of information is about $250 million. So as a comparison, $250 million, essentially for the researcher, free because they use Google Street View data. There's another study, another paper from Science, which showed that researchers could actually very accurately predict poverty levels from satellite image data. And again, here using sort of image data and machine learning models and transfer learning, they could essentially, with pretty good accuracy, understand sort of the levels of poverty of an area. And the motivation for this was, well, one of the huge goals in the world is like trying to understand how to resolve poverty. But if you don't actually know the poverty levels, it's hard to actually resolve the problem. And again, while in the previous case, it was doable, but somewhat cost prohibitive, in many cases for this question, it's just like essentially impossible to actually get this reliably, right? So this is just sort of a few examples to sort of help us sort of wrap our head around the fact that people are using machine learning models and unlabeled and structured data to extract really important measures from this data. But this is only the first sort of like step in this process, right? Because given the extreme success of machine learning models and extracting this kind of data and doing it essentially sort of at scale to use this data, the next sort of obvious question is, if I can extract this information, can I use it for something? Can I use it to answer a question I couldn't answer before? Or can I use it to answer a question even better than we could answer it before? And so what this ends up looking like often is, at a high level, someone using a machine learning model to essentially generate a new variable of interest. And then using that new variable of interest they've created as in a econometric analysis, essentially like a right-hand side variable in a reduced form regression, where I'm trying to understand what the impact of something is on some outcome Y I care about. And now I can I can use models and I can use information I never otherwise could not use before. And so again, this is becoming increasingly popular across the social sciences, across management, across statistical sciences. And so I took a few papers that I had seen over in the literature, sort of doing some version of this to sort of, again, show how it's being used. And so there's this paper from Information Systems. It's the Information Systems literature by Go. And essentially they're trying to answer the question, what is the effect of user-generated content and marketing-generated content on purchase decisions, right? So what they're doing is they're taking a bunch of textual data, using machine learning models to get the sentiment out of all the textual data, and then studying the question of how does sentiment affect people's decision to purchase, right? Seems like a very important question, which drives value for organizations and platforms, understanding how positive reviews, for example, may drive growth in purchase decisions. Colleagues of ours, Francesca Dominicis in the bioscience department at Harvard, and Siflu is an epidemiologist studying this question around pollution. And so the question I have here is they want to understand, how does exposure to pollution for individuals affect downstream healthcare outcomes? A really big question in developing countries. Now, the fundamental problem, though, is that they have sensors in various static locations. And so there are many locations where they don't have sensors. It would be too costly to put sensors in literally every zip code or every block in a country. So they have certain locations where they have sensors where they can actually calculate in real time what the pollution exposure would be. But they have to predict what that exposure would be in other areas where they don't have sensors by triangulating through the sensors they do have. Additionally, they're answering a question they're asking a question about individuals because they observe healthcare outcomes of individuals. And so again, individuals move around. And so again, they have to use machine learning models to actually predict what is the individual exposure of a given person, given these fixed sensors and where those people have been. So it becomes a fundamental sort of question about predicting the exposure to pollution and then studying what is the increase in exposure do in terms of health outcomes later on. Oh yeah, go. No, sorry, please interrupt.
I'm actually know too little about this domain.
Okay.
Since you mentioned predictive machine learning to
Yes.
create new variables.
Yes.
Does it imply techniques such as topic modeling are not part of this?
I mean, so that very well could be, so that would fit as well. So the paradigm is extracting information like a topic, you're like doing topic modeling. And then if you're going to use, for example, some, let's call it some distribution of the topics as your true sort of labels, and then you're building models from that. You're trying to predict, okay, what would this new text I see, what would the true classification of it be? I think in general, we're thinking about more sort of standard predictive models. Topic models could become a part of this if you're using it later, if you're using that as features in a predictive model.
So it does not have to be restricted to unsupervised or supervised learning.
So it's typically going to be supervised learning. So it's going to be supervised learning. So if you use the topic model as inputs to a predictive task, for example, right? Exactly. So if you've built topics and you use those as the features for predicting sentiment, for example. Then you enter this context. But if you're just doing topic modeling by itself, that wouldn't enter this context.
Makes sense.
Make sense? Okay. So far, so good. Makes sense. Hopefully online as well. Feel free to stop me if you want to ask a question. Just jump out. Just speak though, because I won't be able to see you. Okay. And then one more example from recently in labor economics. Essentially here, as maybe sort of as one might believe, the labor economists are interested in the effect of minimum wage. And so what they do is they have this panel of data, the CPS panel of a bunch of households, and they know of a collection of various of minimum wage shocks. So like changes in minimum wage across, I think, for a few decades, maybe 30 or 40 years. The problem is that they don't actually know which households were actually sort of affected or impacted by these minimum wage shocks. And so what they do is they build machine learning models to predict to predict the exposure. How likely is it that your household was affected by this minimum wage shock or not? And then they study, as you become more likely to be affected by the minimum wage shock, what is the change in terms of outcomes for you, from labor outcomes. And so again, what we're just seeing here is that there's sort of a collection of folks across different literatures that are realizing that we could use machine learning to get at some new variables that are valuable for us to study our question, and then study important questions in our literature as a function of that. And again, they couldn't do it before because it either was cost prohibitive or time prohibitive, or maybe just literally impossible to do in a realistic fashion. Okay, and I think we're seeing this happen in our literatures because we're also seeing it happen in our classrooms. This is a sort of paying homage to Carnegie Mellon, where Ben and I both went. A colleague of ours in marketing has a class of digital marketing, and there's this like little part of the course about economining, he calls it, using generating content. So again, the idea is, how can the firms use information that they're generated on their platforms to actually drive decisions on the platform? Again, sentiment of text, viewer data, things like that. And so what we're really seeing is a sort of growth in big data machine learning driving social science research, because we have the ability to answer questions we could not answer before with the use of these models. So that's what I hope I've convinced you of at this point. It's an important question, it's relevant, and it's actually becoming more and more popular across disciplines, across domains. So far, so good? Great. Okay. Well then, I'm going to tell you, unfortunately, this prevalent practice has some issues with it. And I'm going to walk through, I'm going to use as a motivating example, this text sentiment example, to try to show you why this can be a problem, just for demonstrative purposes. So let's say a researcher wants to actually estimate the impact of sentiment on purchase decision. What would that person do? Well, they would go and collect data. Let's say that researcher happens to work at Amazon, for example. They would go and collect a bunch of data for products, the text reviews seen by on those products, and purchase decisions by people who have seen those text reviews for those products. Did they buy or did they not after seeing those text reviews? Like a bunch of this data. And their goal would be the thing they care about estimating, essentially, the ultimate goal is this model. I believe that Y, purchase or not, for example, is some function of the sentiment effects they observe when they go to that website, plus some other controls. And I want to understand what that beta coefficient is. And so fundamentally, though, I have to either go and label every review on Amazon for its sentiment, which would be provably time and cost prohibitive, or I could build a predictive model. And what I would do for this predictive model is that I would actually take a bunch of my review data, I take a subsample of that review data, right? And I go get labels for it. I ask a bunch of Turkers, or I do it myself, or somehow I get labels, true labels for the sentiment of those reviews. And then I build a model that, based on the textual features, predicted sentiment of the text. And then after I build that model, I can then use that model to go to I built it on 1,000 labeled examples, but I have trillions of examples that I did not label. I take that model, I go to those other trillion examples, and I then, in literally a matter of seconds, predict the sentiment for all of those ones I did not label. Because now I have the model labeling on my behalf. And now, with those trillion examples of sentiment of text, controls, and whatnot, as well as outcomes, I can go ahead and estimate this model I care about. And I did. I estimated with millions of data points, so I have a really good, precise estimate of this effect, which is what I want. And so I get an estimate for beta hat and estimate for delta. Pi. for my sentiment and for my controls. And I'm good. Except for this really important fact, is that by definition, I use the machine learning model to label these things. And by definition, no machine learning model is perfect. It's going to have predictive error of some sort, some degree of predictive error. And as a result, if I'm using an imperfect prediction to obtain my value of sentiment that I estimate in my regression, what's going to happen is that means I'm going to have measurement error in that right-hand side variable, sentiment. And what measurement error will do when you go to estimate it in this econometrically will give you bias coefficients here, right? We know that there's sort of three main sources of bias in sort of estimating things: measurement error, reverse causality, or sort of simultaneity, essentially, and omitted variable bias, which are all kind of similar examples of the same thing. And so as a result, if I do this, I have a problem. And so sort of motivate this sort of going forward, I'm just gonna sort of remove sort of sentiment and control sort of thing X and Z, but essentially think about X being sentiment that I care about of text and Z being a bunch of controls. And so this is in fact my problem. I have imperfect model deriving or generating a variable for me that I want to estimate econometrically, but unfortunately is going to have measurement error in it. And sort of just to see this sort of play out, let's take a simple example of a linear regression. And so this is like the structural equation model I'm going to estimate, and recognize that we don't actually observe X. X is the true sentiment of all the trillion examples of text that I have. I don't actually observe X. I only observe the machine learning generated prediction of X. And for this case, just for the example, I'm going to assume X is continuous, just to make it easy for ourselves for some of the math to work out. But we can make this work for non-continuous measures of X as well. So I don't observe X, I observe just X hat. But X hat is not the true X. It is both the true X plus some random noise, some error. And so the regression I'm actually estimating is in fact this one. I want to estimate that one, but I can't. So I only observe X hat on the trillion examples. And so what I'm actually estimating is this one, where X hat's here, and notice in this error is now in my unobserved is now contained in this sort of residual or idiosyncratic noise component of the regression. And that's what's going to create our endogeneity. Because when I go to, and let's say I use OLS to estimate this, when I go to estimate beta hat 1 OLS, what's going to happen is that I'm going to observe that I'm going to see how correlated X hat is with the error term. And unfortunately, it's going to be correlated with it, because this is how correlated is X hat with the error term. Well, remember, X hat is X plus E, as we defined up here. The error term is epsilon minus E beta 1, which means that because E's on this side and E's on that side, it's going to be non-zero. And so by definition, I'm going to have some bias in my estimate. Now, if this was, in the case of a linear regression, and if this measurement error is what we call classic measurement error, where E is essentially independent random noise from X, then this will create what we know as sort of underestimation or attenuation bias. However, if that is nonlinear, which it can be in many cases, the econometric model, or we don't believe that measurement error is classic, which I have no reason to believe that when I use a deep, triply deep neural network, the error it makes will be uniform across all places. I can imagine being really good at some things and really bad at other things. So as a result, it won't be independent noise. Then we have no idea if it's attenuation bias or not. It can be overestimation, underestimation. We have no clue. Okay, so at this point, what I'm hoping to convince you of, and I think this sort of just follows from sort of our basic principles of econometrics, is that while this is a very valuable new thing people are doing, and it has tremendous potential, it has a sort of inherent challenge or flaw in it, that we seem to not be paying much attention to. How we feel about that? Feel convinced? Okay, good. So now, of course, if that was the end of the talk and I was like, well, it doesn't work, guys, and I left, we'd have about 40 minutes of something to fill. So I have some ideas of what we can do about it. I'm gonna try to show you what I think is possible. So let's start with the question of, okay, how would I typically try to solve a problem when I have measurement error? One of the most common ways we try to resolve any kind of bias in our econometric estimation is with instrumental variables. If we had some kind of instrument, we could then sort of resolve this bias in our coefficient. So let's kind of understand what kind of instrument we would need here. So again, this is our regression that we can that we are estimating. Y beta naught, beta 1 x hat, beta 2 z plus this error. And so if we had an instrumental variable W, that variable could be used in an IV regression to mitigate this problem if W was actually had some kind of correlation or covariance with X hat. That is to say, W was a relevant instrument. It has some relationship with W and X hat. And also, W was uncorrelated with the error term here. And the endogenous part of that error term is E, that little e, not the sort of epsilon, but E. And so essentially we need W to be uncorrelated with E. So it correlates with X hat, but not with X hat's error. Okay? And so for W to be correlated with X hat, that would imply that W is correlated with X, the underlying true sentiment of the text, right? Because X has to predict a sentiment. X is the true sentiment of the text. So if we had such a W, we'd be good, right? Life would be great. The challenge is that if any of you do empirical work, instruments are very hard to find. Usually it's somebody in a paper saying, you know, when the wind blows west and then blows from the north and it happens to rain exactly 0.2 inches and I sneeze, then there's a random shock that I could be used as an instrument, so I'm going to use it as an IV. And so we typically argue it from oftentimes very complex scenarios to justify our instruments. Sometimes they're very valid. Many times we're very unsure about their validity. And so this is the problem. Like W sounds nice if we could find it. And I'm going to actually claim, we claim in the work, that if you build a random forest to predict X, so let's say use random forest to predict sentiment of the text, it will actually produce for you potential IVs to correct for the estimation biases. And so this is the claim. It's a pretty strong claim, but I'm going to hope to convince you that it actually has some merits to it in a sequence of slides. How are we doing so far? Doing okay? Okay. So before we talk about before we talk about sort of proving this claim sort of in some meaningful way, let's actually first understand and remember how random forest works. So I don't know people's sort of degree of familiarity with random forest and algorithm. We're just going to have a quick slide on how it actually works. So first, with random forest, if you're trying to build a random forest model, you'd start with training data. So you have a bunch of instances, right? So this would be literally examples of an outcome, a decision somebody made about purchasing a product, a bunch of features about that person, and also this textual sentiment. Sorry, actually, this training data is just for the model. So you have label sentiment for each piece of text. Sorry, each row is a piece of text. You'd have sentiment, label sentiment, and a bunch of other features being like the actual words, for example, of that text. And random forest is going to take this data and it's going to create subsamples of it. So it's going to cut the data into small blocks, both of the rows and of the columns. So we see subsample 1 got columns 1, 2, and 3. And maybe let's say rows 1, 3, and 9. And subsample 2 got columns 3, 4, and 5. 3, 4, and 5. And let's say rows 2, 1, and 5. And then, so within, this last one got columns 2, 3, and 4, and rows 2, 3, and 5. So each subsample has a different sample of rows and columns to it. And then from each sample, we build a decision tree or regression tree, just built on that sample and that sample alone. And then when we get a new piece of text in, and we want to measure, okay, what is the sentiment of this text? What we do is we take these models we built on these subsamples, and we get a prediction from each one of them. They tell me I think this is 0.9 positive. I think this is 0.8 positive. I think this is 0.2 toward negative, right? Get a bunch of predictions. And then the prediction we give as the final measure of the sentiment of the text for a new sample is going to be the aggregation of these predictions. Let's say the average of those predictions if it's continuous, and the mode of the predictions if it's discrete. So this is how random forest is working. Build a model on a bunch of subsamples of data, and in the future take an average or take some amalgamation of their predictions to get our final prediction for a new feature, a new piece of text. Make sense? Questions? Feel good? Okay. And so
usually, I think random forest is a good tool for feature selection, which means you're going to prepare a lot more attributes. So I wonder, for this technique, do you also plan to include a lot more attributes as well?
Well, I mean, I think in this case, the attributes in this case truly are likely going to be like textual features. So like actual TF-IDF weightings of words, for example. You can imagine other contexts though, if it's not text, it's something else. And what I would say is that the question fundamentally becomes if these features are informative or not, right? Do they carry signals? So what has been proven about random forest over and over again is that it's about the intrinsic set of features that are relevant. So if you have 1,000 features, let's say there's 5 features that matter for the outcome, and you give me those 5 features, random forest will do really well. If you give me 5,000 features, of which the 4,995 don't actually matter, random forest will do bad because you're gonna have a bunch of these subsamples that are using features, maybe only features that have no relevance at all. So these models are gonna have poor predictions. They don't use relevant features. And so in a sense, while we're not solving that problem, there is an inherent sort of assumption in using random forest that you are using your features are ones that matter. Now, what will happen in random forest is that it will typically then try to learn features that matter, as you're saying, so which features are the ones that are most accurate, most high in the trees that you pick out. But if you give it too many features that don't matter, it can very well end up creating lots of trees that have no predictive power. So we're going to sort of not address that problem because we're going to assume that problem away in the fact that random forest depends on it. And you've thought about that in the way you built it. Good question. Any other questions? Okay, we'll keep moving along. Okay, great. So this is how random forest works. That's good. But I claim to you that random forest will help us with instrument of variables, and nothing I've said to you so far probably convinces you of that. So let's actually understand. We understand how random forest works. Let's understand why random forest works well as an algorithm. Why does that subsampling, the way it works, actually effective for prediction? So why does random forest work? The first thing is every tree is somewhat accurate, right? The idea is that every tree is using a subsample of the data with labels. And so assuming to Ben's point that you're using some set of features that actually predict the outcome, you're going to predict it better than change. You're going to do a decent job at predicting the outcome because you have actual signal in your subsample to use. So every tree, is somewhat accurate. I won't say it's perfectly accurate, but it, has some accuracy, let's say above 50%, 60, 65, 70, something like that. And the other thing is that different trees, in some sense, will make different kinds of mistakes, right? So essentially, if this tree gets these rows and these columns, but this tree gets these other rows, these other columns, they're using different parts of the data to make their predictions. So therefore, the mistakes they'll make are going to be in different ways. And so what Leo Bremen sort of proved in one of his seminal papers on random forests is that greater strength and diversity lead to more accurate forests. Essentially, what Bremen is saying is that what make random forests work is that the trees all make predictions that are somewhat accurate, but they don't make the same mistakes. They make different mistakes. And as a result, random forests' whole optimization of building the trees is building trees that meet this criteria, that they try to optimize the accuracy and the diversity of the trees in the forest. That's an optimization problem it's solving for. And so suppose then that we had two trees. I'm going to say in a forest. So PI is the predictions for tree 1. And PJ are the predictions for tree 2 in the forest. You have two trees. If you have a forest of 100 trees, for example, you have 2 of them pull out. PI and PJ are predictions that each tree would make. That means you'd also have EI and EJ. That's the predictive errors those trees would make. Okay? So if I had I built the random forest made up of 100 trees. I have my trillion data points over here. I could ask each tree to make a prediction for all those trillion data points. What's your predictions? That's PI. I could ask it to make predictions for PJ. That's PJ's predictions. And EI and EJ are the errors they would be making. What Bremen is arguing is that random forest is designed to make the covariance between PI and PJ relatively strong. That means they predict accurately. They basically are predicting the underlying true value very well. But also that the covariance between their errors is relatively weak. He's arguing that random forest's job is to make sure they make different errors. So they both make strong predictions or relatively strong predictions and weakly make the same errors. That is this is sort of pulled from and sort of interpreted from Bremen's work on random forests. This is what he's arguing random forest has to do. So the question becomes, what makes a good instrument?
So those, the PI and PJ correspond to the sentiment score that we try to
predict for the text, exactly. And then there's some true sentiment score. And so EI and EJ is the difference between the predicted sentiment score and the true sentiment score. So that's the error in their prediction. So the question becomes, okay, well, now we understand how random forest works. What makes a good instrumental variable for us? Let's go back to our regression equation. We're after y, beta naught, beta 1 x hat, beta 2 z, and the error term. Remember that we said that the problem is that x hat's correlated with the error term. And what we'd want is this nice good IV W that would help us resolve this problem. And what W would have to meet is that first, W needs to be not uncorrelated. So W needs to covary with x hat. That's the relevancy condition, right, of I instrumental variables or 2SLS. And W also needs to not correlate with the error, that is the measurement error in x hat. This would be the exclusive condition. That means that W is not correlated with that error term. And so if we had these two conditions met, we would have a very strong instrument for us. And so the key idea is that if we take a random forest that we built and we use one of the trees not the whole forest, just one of the trees as our endogenous regressor. And then we can use any of the other trees as candidate instruments. So essentially, X hat becomes PI, the predictions from a singular tree. That means the error term E here becomes EI, its predictive error. And then PJ, the predictions from another tree, serve as our W. And what we'll see is that what we need then PI, X hat, and PJ, W, to have correlation. That's in fact what Riemann sort of says this random forest is actually doing by optimization. It's giving us two trees are relatively correlated with each other in terms of covariance and underlying prediction. And we'd also need then PJ, W, to be uncorrelated with, or very small correlation with EI, the error term. But in fact, that's exactly what we get from the weakness, right? Because PJ is just, again, some true value X plus EJ, the error term. And so what we really need essentially is EJ and EI, because this is just a constant. This is a true X. We need EJ and EI to have be very small. And again, EJ and EI, according to what Riemann saying random forest is doing, the random forest is optimized to make EI and EJ relatively small. So that's nice. It means that we have, in fact, something kind of smart here. The insight is that if you want to have really good predictive accuracy overall, you should use the full random forest model. But if your question is not just about predictive accuracy, but actually about inference itself, econometrically, it's actually smart to break apart the forest and use parts of it. Essentially, what's happening is each PI is a worse predictor of the outcome than the full forest is. But the way in which it's worse, we can actually instrument for. And so by using the full forest, we get a better overall EI, the error in the full forest is smaller than EI or EJ alone, but these errors are created in a way structurally based on random forest to actually correct for each other. And so it's a very insightful thing to say, if I want inference, if I care about that question, I use parts of the forest. I simply want to predict and forecast the future better, I use the full forest. That's the insight that we sort of derive from this, which is actually quite nice. Now, we have some theorems in the paper, but my talks, I try to keep as much, this might be ironic, I try to keep the math simple as I can, just because I want to make sure everyone in the room can follow us. And so I have a proof of this, but I have a proof by picture, not proof by math, but the math will back up this picture. And so what I have on I built a random forest of about 100 trees. And what I have on the x-axis here is the correlation between PJ and EI. So this is the measurement error in the first, in a given tree, and the predictions of a second tree. So they're going to be essentially 100 choose too many of these dots here. This is for every combination of I and J. That's the x-axis. And then on the y-axis, I have PJ and PI. That's how correlated the predictions of the two trees are. And so what we want, right, is we want, for strength, we want tree pairs that are above 80, 90%, right? Super highly correlated, things up at the top. That's what we want. And we'd want tree pairs where this is at 0, right? And so so now there's a distribution here, right? But what we can see is that essentially PI and PJ is relatively strong, right? There's a lot of stuff above 80% up there. And again, PI and PJ on average, as Bremen said, is actually weak, right? Occasionally it's strong. Occasionally we see things over here and over here. There's a lot of stuff right in this middle part here. Certainly a bunch of pairs, right? Not everything, but a bunch of pairs fall in that category. And so what that means is that there are, in fact, good IVs available. You have to be able to pick them out in some way, though, right? And so if we want to just find a singular instrument, we can do this. We go to this picture and it's fine. Finding things where this is 0, this is 8 and 0.8, and we're done. So take things around here and we're done. But we can even be smarter than that, right? Because the idea is that we don't want to just use one instrument if we can have more, right? We know that we can have multiple strong instruments that actually gives us better and better inference. And so our goal here is to select a set of valid and strong IVs from the pool of all the candidates. And so for this, we rely on a paper from by Bologna et al. This is Bologna, Chen, Chernozukov, oh, I have it here, Chernozukov and Hansen. And basically, they walk through how you use lasso regression for IV selection. And so essentially what their paper is saying is, suppose you have a pool of valid IVs, W1 through WK, predictions of trees 2 through 100. For the endogenous variable X hat, predictions of tree 1. Then what you could do is if you run lasso, you regress X hat on those instruments and keep the ones with non-zero coefficients, then what you're going to get is, what they argue asymptotically is, there's going to be the optimal linear projection of instruments for that endogenous variable. And so then you could run 2SLS on these selected ones and get your actual estimate of the coefficient for X hat. And so we're going to borrow this approach to sort of actually go through selection, because we know they exist. The question is, how do we find the optimal collection of instruments to use for our endogenous variable? So we're going to borrow this. All right. So what I've hopefully just convinced you of at this point is that random forest does in fact generate candidate instruments. It meets the criteria by which we are required to have valid instruments. And that's, in fact, the challenge now becomes finding the optimal combination or set of them, but it does in fact exist within the forest by opening it up. So I want to walk through kind of procedurally how we actually accomplish this by using that idea. Okay, so more pictures. So remember, we have training data, testing data, unlabeled data. So training data and test data are data that is in fact labeled for us. The sentiment of text is labeled for us. We take some part of it for training, some part of it for testing. Then we have a bunch of other data, textual data, let's say reviews, that we have never labeled. Okay? We're going to use the training data to build a random forest, to build our model. We're going to use our test data to evaluate our random forest. And we would use, we would deploy our random forest on the unlabeled data and actually estimate the regression econometrically that we care about on this unlabeled data. This is what gives us the scale, right? We have, the key of this is this size is important, right? That we have, a trillion different textual sets of textual reviews. We only label a small portion of it, but we still want to use the collection of metadata we have to actually estimate our econometric regression. So we need good estimates of what's going on. Okay, so this is our uses. Now, remember that, again, the train data has just labels, right? Because we built it, we use it to build our random forest. The test data has labels and predictions, and the unlabeled data has just predictions. And so let's suppose we build a random forest of 100 trees, right? I'm going to denote their predictions as P1 through P100. And so without loss of generality, we could take P1 as the endogenous regressor, that's at X hat, and use P2 through P100 as candidate instrumental variables. And so the first thing we're going to do is on our testing data, we're going to regress the error of P1 and regress it on the pool of instruments. And we're going to drop the candidates with non-zero coefficients. Okay, so two things are happening here that I want to make clear. Let me talk about the second one first. So if there is a non-zero coefficient, when I regress the error on the other trees, that means that the prediction of the trees correlate highly with the error. That means it's going to be an excluded instrument, right? I'm sorry, included instrument. Because tree 2 makes similar errors as tree 1. That's a problem. We want to make different errors. So when I regress this, if I have non-zero coefficients, it means they correlate. If I have zero coefficients, it means they're likely not to correlate. That's number one. Number two is that there's something happening here. I'm saying I can regress E1, the true error, on a bunch of predictions. So what I'm using here is recall that the test data has labels, because we labeled them, and the predictions. So I can actually take the label and predictions together and give me the error. It's the key here is that the test data has both the true labels, the ground truth of sentiment, because I labeled them, and I have predictions, so I can see what the model's error is on those specific subset of data. And I can use that small amount of data to understand what trees seem to be invalid instruments. And so I keep those around, the ones that seem to be valid, that don't have the same prediction errors as the first tree, I keep those around and call that V1. And then I use both the testing data and the unlabeled data to estimate the second regression, lasso regression, where I regress P1, the predictions of tree one on V1, all predictions of the remaining trees. And here, if I have a zero coefficient, I am going to drop them because they are likely weak IVs. Here, I'm regressing P1 on P2 through P100. And in fact, remember, we want instruments that are highly correlated with each other. And so I've already reduced this down to the ones that seem to have, don't have the same errors. And so now I keep the ones of that are strong, right? I want strong instruments that don't make the same errors. And so I regress P1 on V1 to get what I call S1, which is a set of strong instruments. So we have valid instruments and then strong instruments that are valid. Now, because I run this regression, and I drop some things, I could end up, if I rerun this regression, getting a different set of things that are valid, because regressions are partial correlations. And so if I drop some things from the regression, the correlation of other things may change. So we have to actually iterate between 1 and 2 until we get to a situation where the V1s and the S1s stop changing. They're stable. That means that we have a jointly sort of optimal collection of valid and strong instruments simultaneously. Okay, and that's how we end up getting the set of instruments for P1. Now, but the key is that this is for P1. I can use P1 as a endogenous regressor and find a set of instruments that are both valid and strong. But that's just, what if I made P2 the endogenous variable? I can do the same thing again. I made P3 endogenous variable, I can do the same thing again. So I can let each one of my trees, P1 through P100, serve as the endogenous variable in my econometric regression and find the instruments that most optimal instrument for it. So we do this whole procedure over again and we end up with 100 pairs, P1, P2, P3, P4, all the way to P100, and the corresponding set of instruments, S1, S2, S3 to S100, that are optimal for that given endogenous variable, that endogenous prediction. So now I have 100 sort of pairs of endogenous variable and instruments to instrument for it. And so the estimation procedure, we're going to say, all right, now we're going to use our unlabeled data to estimate the econometric model with the IVs. And I can also, though, just for purposes of comparison, use the labeled data to estimate a regression as well. Now, this regression will be unbiased because it has the true labels. There's no measurement error when you have the actual labels. This regression will have bias in finite samples, but as we know from 2SLS, as you get more and more data, your data will get closer and closer to the truth. And so in a sense, there's a trade-off happening here. I am trading off unbiased, but very large variance because I have small data for potentially slightly biased, but very tighter estimates because I have 1,000 times more data here. Okay? And so we're going to use this sort of unbiased coefficient from this, as we call it, as a benchmark, because it still is unbiased, it can help us a little bit. And so what we're going to do is we're going to use the unlabeled data. We have 100 of these different tuples of pairs of endogenous variable and IVs, and we can do a 2SLS to get the IV estimate using that pair. We have 100 of those, and then we say, okay, listen, we're going to do a hoteling test just to make sure none of these IVs kind of slip through, because it's a regression, right? And so sometimes, even though we're running this lasso, we may end up picking out the wrong thing every now and then. And so we use our unbiased estimate to help us also kind of cut off the tails of that as well, because it still is unbiased. And so it's basically a 2-sample t-test to compare, because we know that beta OLS is unbiased, but we know it has massive variance. We know beta IV is going to be consistent, but have smaller variance. We can sort of test how far apart they should be if in fact the IV was a valid IV. It's essentially like a reverse of a Hausman test, if you know what Hausman tests are. It's a similar idea. And so we use it to kind of help us, again, pin off the sides, but again, it's not necessary, it just helps a little bit. So now we have all of the beta IVs that survive this little test of ours. And so then we pick the one with the smallest empirical risk. We pick the beta IV that essentially has the smallest sort of bias, the mean square, the bias square plus variance. So we pick, of all those options, we pick the one with the smallest variance. And we call this procedure forced IV, what this is. Okay, so I have 5 minutes left. And so I'm going to show you just a quick simulation, and then we'll conclude. So hopefully at this point, what I've convinced you is that there's a problem here, but forced IV gives us some instruments, and there's a way by which we could use the data we have as labeled and unlabeled in a very smart way to get the best of both worlds. Let me show you a simulation. So this is really just a basic simulation. We pulled some data from UCI just to show this. And so this is bike sharing data, where basically we have about 1,000 training observations, 200 testing observations, and there's about 16,000 unlabeled observations. And really the bike sharing data is just a bunch of information about bike rentals in different locations around the city, and activities such as, and weather and seasonal information. And what we're doing is we're building a machine learning model to predict essentially the number of rentals in an hour. So what's the motivation? So you can imagine the question in economics, like as mobility changes, how do other economic outcomes change in an area, right? This is kind of capturing that idea. As you give people access to more transportation, how do other economic indicators change? And so you build a model to predict how impacted they are by this mobility. And then you can sort of kind of actually measure how mobility changes some other outcome, like let's say economic indications of prosperity or cross-pollination or whatever. This is your kind of metric model. Yeah, we just simulate just to sort of show the point. And so again, we just sort of draw things at random. Z1 is uniform, Z2 is binary, epsilon is 0 with a variance of 4, derivation of 2. And again, we sort of they're sort of fixed, so we don't change the regression coefficients. They're always 0.5. This is the one we're after, basically, in our regression. We do 100 simulations, and here's sort of like the picture. And so let's talk about what this picture is showing us. The first thing is beta ML is sort of 0.5. That's a true value, and what you'll see, this is a table with the coefficients and the standard errors. The picture I think says far better and far quicker. 0.5 is what we want. What you'll see is that the red line is the unbiased estimate. It's the estimate using the labeled data by itself. So the 1,000 examples of labeled data that we get no measurement error with. You will notice it is centered at 0.5 as expected, but has a fairly large sort of variance to it. We have biased, which is you pretend like you have no measurement error. People often do. They build a model, a whole random forest, for example, use those predictions from the full unlabeled data, and then estimate the coefficient. So there's measurement error there. So they either don't realize it or pretend they don't have it. And that's the black line. You can see that it's centered far out 0.5, and it's very confident about the wrong answer. Tight, but around the wrong answer. And you see forced IV there. it's not exactly centered at 0.5. It's actually slightly higher than 0.5. It's center. So its mean is not exactly 0.5. It's a little bit off. Check with an ID. But you can see that the standard errors on this is going to be about twice as small as those on your OLS unlabeled data. So again, you are going to get a consistent estimate. It's going to shrink and shrink and shrink toward the right answer. But the idea is that using these machine learning predictions directly in the regression from the full random forest gives you the black line, and those are biased. But our approach will mitigate this in some way. It's not perfect. Again, I want to be very clear. It is not going to be unbiased. It's going to be only consistent. But in 87% of the simulations we ran, there was no statistical difference between the coefficients that Force IV got from the truth. So often the coefficients their confidence interval was overlapping with the true answer, the true one often. So if you were to instead of using the point estimate, you use the confidence interval as a metric or measure for what you think the answer may be in empirical analysis, you have the right answer 87% of the time. And that's very valuable, right? Ideally, because the Force IV estimates are 3 to 4 times smaller than those from the unbiased estimate, because it has access to far more data. And you can imagine in many scenarios, including ones I motivated this with, where the unlabeled data continue to grow and grow and grow and grow and grow, right? You can keep growing it, and therefore you can shrink this variance smaller and smaller and smaller and smaller. Now, again, it will take lots of data, but we're in a world where we have textual data writ large. We have image data writ large. We have data on just at massive scale. And so the trade-off you're making fundamentally in this case is you're saying, listen, would I prefer to have error, this is the red line, that is equally distributed on both sides of the right answer? So it's the error is symmetrical, but have much larger amounts of error? Or would you prefer to have Force IV, which has asymmetrical error? It's not unbiased. The error is asymmetrical. However, the amount of error is far smaller. And what we just show also is that as you get more and more data, we converge to the right answer and the other ones do not, right? So the red line is unbiased because as you get more unlabeled data, unbiased is not changing. This is the confidence interval for the unbiased, centered at 0.5 right in the middle, but it's just going to stay the same no matter how much unlabeled data you get because it's not labeled, so you can't use it for the unbiased regression. The blue line is Force IV. You can see that as we get more and more unlabeled data, it's converging more and more to the true answer. And the black line you can see, which is the biased one, is converging away from 0.5, the right answer. You can see that even more here, that as we get more and more data, the blue line is converging to 0.5 and the black line is diverging away from it. Essentially, the argument is that more data will help us here. For other ones, it will not. And so bias does not go away in larger samples. The IAV estimate will get very close to the right answer. We'll get the right answer with sufficiently large amounts of unlabeled data. And essentially, it's going to be most advantageous when you have large amounts of data. So if you're in a situation where you don't have large amounts of unlabeled data, it may not be as helpful. One thing I'll just say sort of toward the end is that what we found out is that the number of trees do matter. So you simply say, well, why don't you build 1,000 trees, 1,000,000 trees, 1,000,000,000,000 trees? We find is that, again, this is our little simulation study, but there's some convexity to this. So like it got better and better and better to about 100, and then it started kind of dropping off and getting worse again. So there is some optimal number of trees, probably for the setting and the amount of data you have. I imagine if you have more training data, you can get more trees, but we haven't really explored the relationship between that yet. We just know that you can't just keep producing more and more trees as much as you want. So that's one thing I'll say. And sort of, I'll finish up with this, right? That I think it's really important to recognize that one of the major benefits machine learning has brought the world is the ability to actually create these new sources of information that we can use to answer really important, really powerful policy, business, management, economic questions. But unfortunately, what we've done is we've brought in machine learning into a causal inference context without thinking about the tensions between the two. And so what we argued is showing that, and also showing that random forest as a data mining technique can actually help resolve this problem. Because the insight is that random forest, in its definition of what it's creating, in terms of its individual trees, actually creates what we need for instrumental variable regression to work. And so such a property actually lets us use it to discover IVs inside the forest. And so in the end, we designed this procedure, so we made the observation and designed this procedure to pick the IV that is sort of optimal. And this can help us actually mitigate these biases that we get. And so now, what the walkaway is that it's not that we shouldn't be doing this. We should be doing this because it's actually quite valuable to study these really important policy questions. We just have to do it in the right way. And I think random forest is one solution that helps us do that. Okay, that I'll stop. I'll take any questions if we have a little bit of time remaining. I know we're going to 3, so 3 minutes over, apologies. I'll take any questions if they remain, and then we can move on from there.